Oops. Oh, one more. Yeah, feel free to submit a regrade request. I'll look into it. I already looked into a bunch of them. Some of them were valid, some of them were not. So those that we think that we made a mistake, we're happy to change it and make it more fair and more correct. Okay. So let's talk about multi-core systems. That's the last thing that we want to discuss in this course. And today and next week on Tuesday, we're gonna hopefully cover most of the parts. And this is basically what we're going to cover in lecture in quiz 3, including and all the things that we discussed about virtual addresses. Okay, so if you remember, we are at this point, right? We are at the end of our scaling. We hit the power wall, and we want to now talk about a system that's kind of scaled this format that we had. The last thing that I showed you last time was like this modern computer that has a bunch of different components. CPU, caches, DRAM, and then a bunch of different IOs that's connected to some bus. And we also talked about how we further improve our single core systems, and we defined the concept of simultaneous multi-threading, which is essentially saying that if you want to run multiple applications at the time, the simplest thing that you can do is just doing context switching. You run some application for some time, then you pause and run the other application, and so on and so forth. At the most extreme case, you have a question? Okay. At the most extreme case, you can just combine all the applications that you want to run together and run them all together in the same pipeline, and that's simultaneous multi-threading. So we can support multiple applications at the same time, even on the single core. But now we want to talk about what we can do further. Maybe we can extend these into multiple cores and see what happens there. Okay. So the question is like, where are we going to go next? And the story that I want to talk about is, multi-core systems. I want to talk about how do we leverage, multiple cores, the design choices, and of course the challenges that we're going to see in multi-core systems this week and the lecture next week. To give you some idea about like, what are the current configuration of computer systems. I mean, we typically have, let's call it 3 different tiers. We have PC, we have server grade, and we usually have low end, like embedded / IoT device, categories. In PCs or personal computers, what you have in your laptops, you typically have a multi-core system, so 4 to 8 core system. They're typically 4 to 8 wide superscalar processors. All of them are usually out of order. They typically have simultaneous multi-threading, and they typically have 3 or 4 level of cache. Okay, this is the standard that you will see in your computers now. Actually, you can Google and see what exactly are those numbers, because those numbers are usually public. So you can find it for every single CPU that you have. In server grade, what is that being upgraded is typically the CPU. So the CPU gets much more number of cores. So we typically talk about 20 to 50 if you're using an Intel core, and if you're using an AMD core, this goes to even to 100 number of cores. So that's the biggest difference, and as a result, the cache also gets bigger and bigger. And then on the embedded system side of things are getting a little bit smaller. The key criteria here is power, because these are all usually battery held, so energy has to be minimized compared to the others that's kind of like usually hooked up into some source of electricity. Typically we are talking about ARM is the most dominant one in this domain. We are using like M cores and A cores. The difference between them is that the M cores are usually less performant, more power efficient. The A cores are more high-end systems. They're typically in order. A cores are actually out of order. And in this domain, we also typically have both single core and multi-core systems. So even in your mobiles, the CPU that you get is actually a multi-core processor. And most of these systems may not have even a virtual address or operating system at all. Typically, they have like a very simple firmware to kind of schedule things. As others, including, for example, your cell phone, do have an operating system. Android and iOS are the most famous ones in this domain. Okay. Any question before we start multicore? Talking about multicore. Good. All right. So a multi-core system, basically, if you remember when we talked about our CPU or kind of interconnect and our memory system, we had basically this von Neumann model of one CPU and one memory, and then there were a bunch of IOs here as well, right? So that was the model that we so far we talked about. The multi-core system is essentially kind of increasing this number of cores to multiple of these cores. So instead of just having one CPU, now we have, for example, 4 CPUs or 8 CPUs. The biggest thing is that since you have multiple cores cannot usually be on the same chip, right? So what you will do is that now you have multiple different chips, and in order to connect these into your memory subsystem, you need kind of a wiring or interconnect between them. This interconnect is different than what you will get on chip, which is much more faster because you have to go further distance. There will be a different technology for doing the connection and so on and so forth. And as you will see, we need to not only like have a connection between your cores and memories, you need connection between cores and cores, and all the variation or permutation of this connection needs to be there too. There are a whole bunch of discussion on what to do with interconnect, what is the right interconnect, what is the correct network to use, and so on. Part of it you will see if you take any network class, but we won't go further than that, and we just refer to a future course. If you are interested, you have to read it yourself, okay? But just keep in mind that there is an interconnect that's sitting in between, and it has actually a quite impact on the system because so every communication has to go through that, okay? So the biggest question is, okay, why do we need multi-core, right? And the short answer is we get two things from having a multi-core system. The number one is what we call multitasking, and the second one is what we call a thread level parallelism, all right? And these two things are not the same thing. And in order to understand them, you need to know a few things. First of all, the multitasking, if you remember, I told you that we are using simultaneous multi-threading, right? So we're basically having a superscalar system, bunch of different applications, and try to run them on these different kind of like lines, right? Different superscalar lines. What multicore gonna give us is basically duplicating this into kind of multiple of these. And what it does, it means that now I can run more applications at the same time, right? So if I have one worker, I can do one. If I have two workers, of course, I can do two. Within each worker, which is the CPU, you can have simultaneous multi-threading. So technically, for example, if you have a 4 issue, you can run 4 parallel programs. So if you have, for example, 2 cores, you can run 8 parallel programs and so on. And the reason that this is important is, these days, it's very, very common that especially at the user level, market domain, there will be lots of things that you do at the same time. You have multiple tabs in your browsers, you listen to the music, you type on something, you watch a video, you do all those things at the same time. Your email is being checked at the background, your news is being checked at the background. So there are lots of things that are going on the same physical device. So what you really need to do is being able to have a computer that can run these things in parallel without any disruption, right? If you only had one core, what would have happened is you had lots of context switching, and context switching, has lots of overhead because it has to pause, the app, the execution of one instruction, and then it has to switch to another and switch to another and so on and so forth. But the problem with that would be that, one application will take now more times because you kind of like, need to pause. On the other hand, if you have multiple cores, then you can just, without any disruption, you can run things, right? There are a whole bunch of things about multitasking, including like, what's the best way I schedule this applications on different cores? What is the kind of the balance between power and performance. What about heterogeneous systems that we have, multiple different cores with multiple different functionalities? Maybe some of them are faster, maybe some of them are slower, and so on and so forth. So there's a whole bunch of, design challenges and trends there, which we're not going to particularly talk about. It's more of a course for your real-time system or an operating system course that will talk about this. But just keep in mind that one thing that's multi-core system will give you is multitasking and faster multitasking, because you just have more options to run more things. Okay. The second thing that multi-core going to give you, and that's actually particularly what we're interested in, because that's what really contribute to make computers faster, is if we're given one program, how we can distribute this program into multiple cores, run in parallel, so that we actually get n times faster execution time of that program. If you remember about the plot that we showed, we kind of like show it this way, right? We said that essentially as the time goes by, the performance goes up, right? And this performance is the performance of the single application. It wasn't the performance of multiple applications. And we said that generally, like, doing out of order or branch predictors and so on and so forth help us to make this performance higher and higher. But if you have multiple cores, all of them have the same speed, adding more cores wouldn't give you more performance, because if one application is assigned to one core, doesn't matter how many other cores you have, that application, the execution of time of that application always is the same amount. So the question is, how can break down this application into multiple pieces and run this in one core, run this in one core, run this in one core, and run this one in one core. And if this thing can happen simultaneously, then I will get 4 times faster the speed. So it's as if that one of my cores is 4 times faster. Okay, so that's the idea of what we call a thread level parallelism, because we are dividing the program into multiple threads, and these threads are being parallelized and run onto multiple different hardware. All right. To give you a basic idea, let's think about, we want to just add 64,000 numbers together. Okay. And let's say we have 64 processors. The easy way to create a software to run this application is, we are basically saying that, okay, each application takes 1,000 number of these 64,000s. So we create a group of 1,000 numbers. Then we're going to say, okay, each processor locally do the summations, the partial sums inside your processor, right? So these 1,000 summations happens in parallel. So there will be a loop that basically just sum this number and it's repeated 1,000 times. And this PN is basically the ID for that processor. It basically just a clever way of saying that your portion of data is the portion based on your ID. So processor 0 gets 0 to 999, processor 1 gets 1,000 to 1,999, and so on and so forth, right? So if you follow the code, you will see that basically all it does is that if my processor ID is 0, I'm gonna automatically just reads data that's assigned to me, right? So we can just simply assign IDs for the processors. That's what operating system will do for us. And this way we're going to have this partial sums per processors, right? There will be a sequential part that we need to gather all these values, all these partial sums. So there's hundreds of there's 1,000s of these partial sums. One of the processors, think about it as kind of the master, the one that's orchestrating this. So that processor going to ask all the other processors that send me your partial sums. I'm going to sum them together. And that way I can have the final value, right? But that part is much, much, much smaller than the part that we are parallelizing, right? If you remember Amdahl's law, we told you about that, each program has 2 parts, a sequential part and a parallel part. And we said that this sequential part is the part that no matter how many cores you're going to have, you cannot, improve this. This is basically this, for this example, this is the part that you need to gather the partial sums. No matter how many cores you have, at the end of the day, you need to add them all together, right? So that's the sequential part. But hopefully, if this this parallel part is the significant amount of this program. Let's say this is like 95% of the program, and this is only 5% of the program. If you remember with the Amdahl's law, we're basically saying that it was kind of like be 1/1 minus the sequential part times the number of cores. So for example, what we were gonna get is we're gonna get something like in 95 if the number is so big. So we're gonna get something like 0.5, like 20 times faster, for example, right? Is it 20 times faster? Yes. So what it does is that the sequential part divided by the number of cores here, and then assuming that this number of cores is really big, that's the number you're gonna get. So basically, what all this says is that you are bounded by this sequential part of your code, and that if that sequential part is moving towards 0, you basically can infinite amount of parallelization, right? So that's kind of like the idea. Any questions? So how do we write programs to kind of like extract this thread level parallelism? So that's not a trivial task to do. It's usually actually writing parallel programs is very hard, especially now that we know that we're kind of bounded by this sequential part. So we really need to write not only good algorithms that can extract the parallel part, but you really want to write algorithms that kind of minimize this sequential part, right? There are ways, probably some of you have know or seen this before. There are specific algorithms, including like MPI or pthread. CUDA also can be used in this case. And then there's a whole bunch of problems with the communication and sequential parts that we need to look at. So generally what this means is that if you add n more cores to your system, you're not going to probably get necessarily n times faster a system. But hopefully, if you can at least n over, I don't know, 2 or maybe even better, that's what you would be happy about, right? So you can put more cores, and you eventually get a faster system. In reality, what will happen, unfortunately, is if you don't fully utilize your systems, no matter how many cores you're going to get, there will be some cores that are doing more of the work, and they will be the bottleneck of your system. So improving this requires better algorithms, requires faster communications, and all those things. This is an entire field of study called parallel programming and parallel computing, that if you're interested in these kind of things, I recommend either taking a course in this domain or reading a book about this. We're not going to go further than this, but there are lots and lots of applications in bioinformatics, in weather prediction, in machine learning even, that could use parallel programming. So it's not like our everyday application use parallel programming, but there are lots and lots of scientific applications that typically use parallel programming, and that's what it's important for us. So industries actually use it pretty well for many of the problems that they have, and that's the way that they're going to get improvement in their systems. Any questions? All right. So now we know that what is the use case for the multi-core system. Now let's actually talk about how to build a multi-core system. We're going to talk about the design decisions and the challenges. And remember, in both cases, in any cases, the goal is that we want to either improve the multitasking speed, or in most cases, we want to improve the thread level parallelism speed. Okay. So comparing single core to multi-core, we first have to know what really changed, right? What we need to think about. That's like, when we're saying, oh, we have multi-core, what are we talking about? The biggest thing that changed is our interaction with memory, okay? Why? Because while you kind of like, create more memories, create more cores, you cannot duplicate your memory. You can make your memory bigger, but your memory infrastructure is still one memory infrastructure. So you have a bunch of cores, and you can extend this as much as you want, but the memory subsystem should be 1. And the reason that we need the memory system to be 1 is because we want to share values. If you don't share any value between the cores, then you cannot parallelize things, right? So if this core has its own memory and do its thing, and the other core has its own memory and do its things, how do you want to share these values together in order, for example, to do the partial sum or the sum or any other things? If you don't share anything, it's as if that you have one laptop in your home and your friend has his own laptop in his home, right? So it doesn't have any multi-core system, functionality to it. Multi-core and generally thread-level parallelism makes sense when you start to sharing data together. So that's all these problems that might arise, that you have one memory shared between multiple cores. So let's see what happens. How are we going to mess up this system, basically? Okay. So the biggest two question is that, okay, now that we have one memory, how do we share the main memory among the cores? And more importantly, how do we share the cache between these cores? That's the two things that we want to talk about in this lecture. There are two options, well, actually 3 options that you can use in order to share your caches and your main memory. The first one is called shared cache. All you can do is that say, okay, I'm going to just give the same amount of cache to everybody, and everybody can just fight for the cache. So the design would be that the cores will sit here. Since they need to talk to each other and they need to talk to the main memory, the cache then needs to be outside this chip here, and there will be an interconnect that kind of like connect the caches to the cores, and then we will have our memory system also shared among everybody with the same format that we share the cache. Okay, so this is like a shared cache model. The other extreme is saying that, okay, no, we're not going to share the cache at all. We're going to have a private cache for every single core, but we're going to share the main memory. So if you want to share something, just put it in the main memory, and then we're going to read it from there. But my cache is that don't mess up with my cache. I have my own cache the same way that I had before. And if I need to read and write something from my main memory, I'll put things in my private cache, and that's it. Okay. The biggest difference between the two is if you think about our miss penalty, our miss rate, and hit time. Let's see what happens in each of these two different structures. And finally, think about the sharing and how easy the sharing would be in each of these two things. So when we are talking about hit time, which one do you think has a better hit time and why? Any suggestion? So the private one has a better hit time because it doesn't have to go through all the way to the interconnect. So this connection here versus this connection is much more faster because it's actually on chip, versus the other one has to travel to the interconnect, go somewhere else, and come back. Right? So the hit time, private cache is much more faster comparing to shared cache. Okay. What about miss rate? And for miss rate, consider two scenarios. The first scenario, consider what we call a cache friendly, which means that if you have multiple applications, all of them fit nicely into their cache. And the other scenario, think about what we call a streaming application, that the application itself doesn't fit into the cache. So in the first case, which one do you think it's going to have higher miss rate? The private one or the shared one? If the applications kind of fit nicely into the cache. So you're saying shared one is going to have more miss rate or less miss rate? More miss rate. So somebody says that shared one is going to have more miss rate. Any other idea?
Are we assuming that the sizes of the tag, of one private and one shared, is the same?
So the combination. So the question is that are the sizes so the combination of private is same as the one shared. So I'm dividing this into 4 to make those private. So what will happen is if the applications are kind of like wants to fit nicely in the cache, shared one is actually a better idea. The reason for that is that let's say, you know, you have 4 different applications. This application use this amount of the cache. The other application maybe use this amount of the cache. The other application maybe use this amount of the cache. And the other application maybe can use a little bit more of the cache in order to, like, you know, fully fit into the cache. In this scenario, this core number 4 gonna suffer a little bit of performance just because the cache is a little bit small for it, right? But if we had shared the cache among all of them, if you just combine these numbers, let's say this one is like 75% and this one is like 50 and so on and so forth, you will see that all of them nicely fit together in this shared cache. And this extra space can actually be assigned to cache number 3. So cache number 3 could actually use more cache. So instead of like every cache just get 1/4 rigidly, all the cache can kind of fight each other in order to have more space. And if we have a cache-friendly applications, that would be in our benefit because we are utilizing our cache better, right? It's kind of like very similar to fully associative versus direct map idea. So this is kind of more of a direct map. We are just assigning rows to each program. And this one is more of a fully associative. So if you have lots of conflict, this one can perform better for us, right? So in cache-friendly applications, shared is actually better than private. But on the opposite, if we have one application that's very aggressive, the application that doesn't really need cache, but it needs a really, really big amount of cache in order to, like, you know, satisfy the access pattern that it has. It's kind of like those applications that start from 0, go all the way to the address 1000, and then come back and do it again and again and again, right? These are kind of like what we call a streaming application. If that's the case, then sharing gonna completely mess up our performance, because not only this guy gonna use the cache because it's even this one is not enough for it, but gonna also like evict everything else, every other useful information from cache core 0, core 1, and core 2. So everybody gonna suffer just because this guy needs to use a bigger cache. And if you don't use any sort of, you know, algorithms for fairness between, you know, how each cache can use this, which typically for shared cache we don't, then everybody gonna suffer from this. So in that case, private is actually a better option than the shared cache. You got a question? You have a question? So the question is, wouldn't, if you have a private cache, wouldn't have you the problem of if somebody writes to a shared data, the other caches needs to update themselves, and that's exactly what we're going to talk about this. So you're spoiling it, but yeah, that's a very good observation. Any other question? And then the miss penalty in both cases is going to be the same, because again, if you remember, the miss penalty is the time it takes to go down. And actually, miss penalty for this one might be slightly less, because in this case, miss penalty has to go through the interconnect. In this case, we already paid that penalty. So miss penalty in this case is slightly better. And sharing, if you think about sharing, actually then going to be much more easier in this case, because as you pointed out, if both cores wants to write and read into something, in this case, it's easy to write and read something here because we only have one copy of it, right? And this copy is accessible, for example, by this core and this core. In this case, though, the copies has to be local. So we will have a copy here and a copy here. And if something happens to this one, we need to kind of like also, you know, inform the other one, right? So the private cache needs to handle that. So sharing for this one is better than this one. Okay. So combining all these things, the idea that we're going to use in modern system is that given that, you know, there are good things about the private cache, there are good things about the shared cache. So why don't we use both? And we are leveraging the fact that, you know, caches are inherently a layer by layer design. So what we can do is that maybe we can say, oh, the level 1 cache can be private, But LLC last level cache like L2 or L3, this one can be shared. So our system is a hybrid system where part of my cache, typically a level 1, which we need the highest, the best hit rate, would be private, because remember the hit rate is very, very important for us. So we're going to have a private cache and private L1 cache for each core. But given that we need sharing and we need better miss rate and so on, the bigger cache, the L3 cache or L2 cache, going to be shared among everybody. So everybody going to like fight for it if they want to. And in all cases, the memory would be shared among all of them. If you remember the page table, and we had like, auxiliary bits that tells whether this page is shared or not, we will add that flag. So if it needs to be shared among the processes, we just add that flag into our system. Okay. Any question? All right. So that's it, right? So multi-core systems, shared cache, private cache, and that's it. We are happy, right? We're going to get what we wanted and nothing else happens, right? Well, what happens is there are going to be two class of challenges with this approach. The first is this type of private caching and shared caching could lead into correctness issues. There will be two correctness issues that we're going to talk about: the consistency problem and coherency problem, which in this lecture, I'm going to talk about the coherency one, and the next lecture, I'm going to talk about the consistency one. And it's also going to lead into performance issues, because as I said, if one program becomes so greedy and try to like kind of hog the entire cache, the other is going to suffer. So we need to kind of like, maybe detect these behaviors and do something about it. The second part, we're probably not going to have time next week to talk about it. We might talk about it a little bit in the week 10. But this first part, we're going to focus in this lecture, the rest of this lecture, and the entire lecture next week. Okay. Any question? Okay. So let's see what are those correctness issues. As I said, there are two things that we need to talk about. The first one is what's called a cache coherency problem. So what the cache coherency problem will tell you is that there will be scenarios that a specific line in memory has to be shared among multiple caches. But really what happens is that these two copies are not coherent. They're not the same thing. I'll talk about it why. This is like, an example to see why we were going to have a problem like this. Let's say we are focusing on one particular line in memory, the line Z. Z could be any number. Let's say 200. And then let's say we have core number 1 and core number 2 that are sharing this line together. They're part of the same application, so they obviously want to share to it. And let's say that there is a timeline like this, that core number 1 first tries to load Z. Okay, so if you're loading Z, if it's not in the cache, if Z is here, the first thing that might happen is that, core number 1 going to cache Z into L1. Remember, when we are loading something, we're going to put it in L1, right? Because we want to have it in future. So far, so good. Core number 2 also, after a few instructions, decide to also load Z. So core number 2 is also going to go through the memory and bring Z. And in this case, both of the Z's are, let's say, initially are equal to 0. So this one is, so this one is equal to 0, and this one is equal to 0. So we are happy, right? So nothing bad happens. Now, after a while, core number 1 going to decide that I want to update this value. So I'm going to write, for example, 100 to Z. So what will happen is that core number 1 going to start writing things to the cache and say that, okay, Z now should be equal to 100. Similar way that we talked about in the project, if you're using a write-through strategy, we're going to immediately also update memory and tell memory is equal to 100. If you do a write-back strategy, we're going to keep this internally in the cache and not even tell the memory. And then the next time that core number 2 tries to load the same Z, the core number 2 going to first look up into its own L1 cache and see that, oh, Z is here and Z is equal to 0. because that was the last thing that's core number 2 has seen. So at this point, x6 is gonna get 0. Whereas since these are the progression of the program we had assumed, in this part we had to get x6 or z equal to 100, right? And that's the problem that we call cache coherency, because the copy of the z in core number 1 and in core number 2 are not the same thing, because at some point during the execution of this program, one of the cores decided to write. And if we don't do proper updating and announcements and tracking, there is no way that the other cores will know that this value has been updated. Why we didn't have that problem in a single core? Because in single core, we only had this portion of the system. If you read something, you will read it from the memory. If you write something, you are the only one who are writing to that memory, right? So you're not going to have the coherency problem because you are the one who is actually accessing that data and reading that data. So they're not going to be happening like that. But if someone from outside come and write something to your memory, then you're going to have the coherency problems, right? So you need to come up with ideas of how to solve this issue. Any questions about coherency? All right. The second problem that we're going to talk about is the consistency problem. People often, mix up these two. The consistency problem is about ordering. It's not about the values, but it's about the ordering. So what will happen is that, let's say we have an example like this, that we have two cores, kind of similar to what we had before. So let's say that core number 1 and core number 2 are sharing two memory addresses, Z and Y in this case. Let's say in first core, core number 1 first loads Z and then writes to Y. So load from Z and writes to Y. And core number 2 do the opposite, load from Y and write to Z. All right. And then if loading is going into X2, and in this case, loading goes into the X1, the question is, after running these two applications, this application that's kind of parallelizing to this course, what would be the value of X1 and X2? Any suggestion of what the value should be? Assuming that, your X8 is 100 and X7 is 200. Well, the answer to that is what the consistency problem is, because we don't know the ordering of what's going to happen between these things from the memory perspective. What we do know is this should happen before this, because this is within one application and we are kind of like doing in order within one application. We also know that this should happen before this, so this should happen before this. But the interleaving between these two, we have no idea that's how it's going to happen, because these are two independent cores. They have no way of talking to each other and saying that, oh, let's synchronize, or I will do this and you do that, and so on and so forth. So what will happen is, for example, maybe we run this first, then we run this second, then we run this, and then we run this. In this case, what we're going to get is, let's say Z and Y are initially equal to 0. So at this case, if we have this kind of like, sequence, X1 going to be equal to 0. Then we're going to write X7 to Y. So Y going to get equal to 200. Then we're going to load 200 to X2. So X2 going to be 200. And then we're going to store X8 to Z. So Z at this point is going to get 200. So after running this, X1 going to get 0 and X2 going to get 200, right? But if we actually do it differently, if we run this first and then run this, we're going to get different values. We're going to get X2 equal to 0 and then X1 equal to 100. And even more confusing is, if we are doing this first, then this, then this, and then this, in that case, what you're going to get is X1 equal to 0 and X2 equal to 0. And this is, all of these are completely possible and valid because nothing prevents you, because these cores are, again, two independent cores. When you start running the program, both of them start from the beginning. There might be some, stalling happening in between for one core, but not happening in the other core. So you have no idea of like the timing of these two instructions because these are happening in parallel. So you have no control of which one going to come first and which one going to come next. All right. So at the end of this, it's very hard to say what would be the value of x0 and x1. And more interestingly, if you run this multiple times, chances that you get different values is actually pretty high. So it's because that the initial conditions might be different. So one core might be faster than the other core. Next time the other core becomes faster than the other. All right. Is that clear what we're going to get different values for x1 and x2? All right. So we're going to talk about this synchronization problem a lot next week. There are lots of different things that we need to talk about, but let's talk about consistency first. To just summarize what we have said so far, we're going to have correctness issues and performance issues in the multi-core systems. In correctness issues, we're going to have a coherency problem, and we're going to have the consistency problem. I'm going to talk about this today, and I'm going to talk about this next week. If we have time, then we also might talk about this performance thing next week as well, because that's not the correctness issue. That's more of like a quality of service issue. All right. So let's talk about the coherency. To remind you one more time, the coherency issue is when we have multiple copies in the private caches, one of the private caches updated, but the other has no idea that it has to be updated. So it has what we call a stale copy or a wrong copy of data, and that entirely messes things up. So that's, as I said, this is a correctness issue. It's not even a performance issue. So we need to really, really fix this issue. So why we have a cache coherency from the beginning? It's because we have local caches, right? So you might ask, okay, why did we have local caches to begin with? If you recall a few slides before, I told you that we want private caches because it has a better hit time, it gives us more fairness, and so on and so forth. So we really want to keep our private caches. We cannot remove that. If we had removed that, then we never had the coherency issue at all, because all of them are sharing the same line, and that line is being written to the cache multiple times. So if we didn't have sharing or didn't have private cache, we didn't have a coherency problem, but we cannot eliminate any of these two. We need to have sharing because there is one application that needs to be shared among the cores if we want to get performance. So we cannot, remove the sharing. We cannot remove the private cache either because private cache is good for our performance. So we cannot remove this as well. So we really, really need to solve this problem of cache coherency given this particular infrastructure. Right? So what is cache coherency? Let me formally define it for you. So we call a memory system coherent if we have three things. All right. So I'm going to just read it out loud. So if you are reading from an address X from a core P1, the value that is being returned to P1 has to be the most recent write to X. Okay. So what we say is that if you're reading something from any of those cores, we have to get the most recent value that's written by any of the cores. All right. Very simple, intuitive. That if you're reading something, we are expecting that this value that I'm getting is the most recent value, either written by me, myself, or by any other course. If we're not getting that, we're going to have a coherent problem. That's number one. The second thing is that we call it, so this is what's called read what is written. Okay. That's kind of like the examples that I gave you. The second one is that the coherent writes should happen eventually, which means that if P1 writes to X and P2 reads X after a sufficient time, and there are no writes in between to X, P2 has to read what's been written by P1. Very similar kind of to what we said here. But what we are saying here is, in this read what is written, is we are particularly focused on one core. And here we are saying that, if there are multiple cores, P1 and P2, or generally PI and PJ, if PI writing something to the memory after a sufficient time, and I'm going to talk about why this statement is important. If P2 tries to write the same line, it has to read the value that's been written by PI. So PJ has to read the value that's been written by PI. Okay, so this is the coherent write. And the second one is what we call a causality of writes. So if you have multiple writes to the same location, those writes has to be serialized. So if core number 1 writes first and core number 2 writes second, what we should see at the end of this is the value that's been written by P2. And remember, this is very similar to what we discussed in out of order execution. And we said that, things should happen in order. But remember, between the cores, we have no way of doing that using ROBs or things like that. ROBs is per core, per physical thread. What we are talking about now is two physically separate things that actually literally physically at two different places. And we need to kind of make these two synchronized, make these things two coherent. All right. Any question about this slide? All right. So that's what we want to get. So the first question is, okay, can we actually write software such that we don't have coherency problem? And the short answer to that is no. The reason is that the software developer typically have no idea about what is happening in the cache. You don't know what is the size of your private cache. You don't know what is going to be cached and what is not going to be cached. So you cannot really control when you're like, writing your partial sum code that's saying that, oh, this part cannot be cached or this part can be cached. What you can do is actually, well, the answer to that, whether software can do it or not, is more of a maybe answer, because in some specific ISAs, including x86 for Intel, there are instructions that can flush things from your cache. Okay, so what it does is that if you use that CF flush, that particular line of memory can be flushed from the cache. So you can actually make sure that that line is not cached in your memory. So at least you know that this is not available in any of the cache. So we kind of like you're eliminating the question from the beginning. You're saying that, okay, I'm not going to use the cache, and in order to not using the cache, you are using this instruction. Okay, but this is very, very inefficient, because for every single line that you want to share, every single time that you want to access that line, you have to kind of do this, right? And this is not the very best and optimal way of doing this. Another thing that you can do is ask OS to not cache it for you. So there is also a capability, usually in most of these modern operating systems, that allows you to not cache a particular page. Remember when we talked about IO, for example, we said that IO is not cacheable. You can do the same thing here, but again, it's not something that you typically write in your program. In your program, you just write your code assuming that this will work in hardware. So what we really need to do is a solution in hardware. We need what we call coherency protocols, which essentially what it does is that we need to know exactly what to do after every single load and after every single store, after every single load miss and after every single store miss. And it's more of like a idea of see something, say something kind of thing, where each cache, if there is a request coming from their own core, they kind of have to tell everybody else that what's going on, and everybody else has to update themselves based on what's going on. Okay, so that would be kind of like the idea. The rest of this lecture, I'm going to talk about this idea in actual concrete steps. All right, so we're going to use hardware to track lines for every single cache. All right, and we're going to call this what we call snooping behavior. So every cache going to snoop the rest of the activities that's going on in your system, and based off that, it's going to invalidate or change things in its own cache. Okay, to give you an idea, this would be the design that we're going to have. We're basically going to have our CPUs or cores here. So I'm just rotating my image. we have our private caches here. So these are all private caches, and we might have multiple of them. Then we're going to have, if you remember, the memory bus, where our main memory, our disk, and our last level cache are basically sitting here. What we are suggesting is that if something happens here, this cache is responsible to tell everybody else that I did this. That, for example, processor 1 asked me for address Z, or process number 2 asked me for address Y. So everybody else, not only you broadcast that information, everybody else snoop your cache, that behavior, and then gonna sit, like, get that information and do something about themselves. So if they have that copy, they might invalidate themselves. If they don't have that copy, they may change the values and so on and so forth. All right. I'm gonna pause here, and I'm gonna give you a few minutes to have a break, and then I'm gonna come back and then talk about the actual details of this. All right. Okay. So let's continue. So remember, we want to basically, for every line that we have in our private caches, for all the caches that we have, all the private caches that we have, we want to keep track of things. We need to store some bits. All right. I'm going to describe what those bits going to be, but we're going to store those bits. You might ask, where are those bits are stored? So they're going to store with your lines, with your cache lines. And think about it as similar to your LRU states. The same place that you're going to store those, you're going to also store your coherency states. All right. So we're going to call this coherency states. Question?
The unit, the biggest line of the first cache, where it says each unit broadcasts, is it the cache that's the broadcast?
Yeah, unit is cache. The question is, like, unit in this this slide is a cache. Yes. So we're gonna store it there. All right. And typically we call this metadata for each line. So each line has the tag and data, and it also has metadata for all these other things. Okay. So let's see, what should we do, kind of like what happens in our cache, Snoopy cache coherence. So I mean, the basic things that we can do, and then after this we're gonna add more things to it, is that if there is a write miss, which means that I as a core wants to write something to my cache, and the data is not here. So I want to write to it and the data is not here. What I can do is I'm going to broadcast as a cache, going to broadcast to everybody that this address Z, for example, is being written. So all these other caches will see that. And what they can do, as one of the things that we will do, and as I said, we're going to change this a little bit as we move forward, is that everybody else can just invalidate that value if they have it. So there could be in some scenario that caches don't have that value, but if they have that Z, they have to invalidate it from their cache. They just have to get rid of that value. Why? Because this value is going to be overwritten, right? It's going to be updated, so there's no longer makes sense for me to keep track of the old one. If I just invalidate it, get rid of it, the next time my core wants to read this, we'll go through the main memory and bring it, and we are happy, right? So on the write miss, all I need to do is broadcast the address and the intent for writing, and everybody else will see that address and that intent. They're going to internally look into that line in their caches. If they see that line, they're going to invalidate. All right. So that's what will happen on the write miss. On the read miss, what will happen is that, again, I'm going to have a core and a cache, and then the other ones also have their caches. Read miss means that I want to read this Z, but it's not here, right? So what will happen is that I'm going to broadcast the intention of reading, and I'm going to broadcast the address. If everybody else has that value, they have two things that they need to do. Since I want to read this from the main memory, it's important for the other caches to, if they have the updated value, if they have what's called a dirty value, they have to write it back to the main memory before we are servicing this request. Why? Because if this value is updated in this cache, but it's not updated in the main memory, remember, this is the write back strategy where we said, if we are writing something to the cache, we're not going to update the main memory. We're going to keep that and then update the main memory later. This cache has to quickly go to the main memory and update the main memory before this value is being read from the main memory, right? So if the line is dirty, you have to update the main memory, and everybody else has to basically invalidate themselves. Yeah.
Have the line being dirty but have different values in it, then which one is correct?
So so the question is that if there are two different cores that they have the line dirty, what will happen? It's not going to happen, because we will talk about like in the actual cases. But if somebody wants to write first, everybody else will gonna get invalidated. If the next person gonna write, it's going to be a write miss, so everybody else is gonna get invalidated. So it's not gonna, you're gonna have two dirty copies in two different cores. So if it's if it's dirty, I have to just update the main memory. If it's not dirty, then I don't need to do anything, because this is a read. So it's going to read from the main memory the correct copy. I already have the correct copy, so I don't need to do anything. I just sit still and do nothing. So it's either in my cache and I have a clean copy, I do nothing. I don't have it in my cache, just ignore it. I have it in my cache and it's dirty, so I'll just update the main memory. All right. And in all these cases, then the updated value will be read and put into the core. Okay. So let's see how this helps us with the examples that I gave you. So if you remember, we had Z here. And so this was a read miss. So we're gonna broadcast this. Nobody else already has it, so they just ignore and disregard this. So we're gonna just safely read the correct copy of Z. Then this one comes in, and this one is also read miss for core number 2. Core number 2 gonna announce this to everybody else. In this case, core number 1 has it, but it's not dirty. So core number 1 just disregard this message safely, and we're gonna read it from the main memory and put it here. So these two are good. Then we're gonna have a scenario like this, that we're gonna write something to the main memory. So in this case, we're gonna change this Z to Z prime or something like that. It's not a write miss, it's just a regular write. And then the next time this reads comes in, and it's going to be here, but this guy also see that this is a read. So what they need to do is that since they have a dirty copy, they have to actually write it into the memory and inform that memory that this value has been updated. Okay. So basically what will happen is that if you have a dirty copy and you see a read miss or read hit, actually this case should have been miss or hit. What will happen is that you will kind of intervene and update the memory and tell that everybody else has to basically do that as well. All right. And this way, what will happen is that we are guaranteeing that this value that's X6 gonna get is that this value that core number 1 has written into my cache. Okay.
Why can't we just forward the value rather than having to go on the save us?
The question is, why don't core number 1 just forward the value to core number 2, and you're actually getting there? So we're going to add these things to the whole story. Going to be these kind of things. All right. So the minimum we need is basically 2 states. All right. The modified state, or the valid state, we call it, which basically I have the valid copy of that value. And the second state would be I don't have that value at all. right? It's invalidated. If I have these two, I can create a cache coherence protocol to kind of like make sure that we never gonna have cache coherency problem. So we call this MI coherence protocol. M for valid or modified. We call it modified. I'm gonna describe why. And I for this invalid one. All right. So if you have an MI coherence protocol, we're good to go. We can fix this issue. To give you an example, let's say we have 3 cores, okay, and each core has, let's say we are talking just about one specific line, line Z, but this repeats for every single line in my cache, okay? So let's say for line Z, we have 2 states in core number 1, 2 states in core number 2, and 2 states in core number 3, okay? And then let's initially say that all of them are in I, okay? So I'm initially in I in all of them. And then let's see if we have a bunch of different sequence of instructions, what should we do, all right? So the first thing that we can do is, for example, core number 1 reads. So I'm going to show it this way. I'm going to say R1, which means that core number 1 wants to read, okay? Since core number 1 wants to read, and all of them are in invalid state, means that nobody has that data. So what will happen is that core number 1 going to switch from I to M, okay? So if reads is going to go from 1 to from I to M, right? And everybody else just stays in I. They don't do anything, right? So initially we had I. Then after core number 1 reads, this one going to go to M, and this is going to stay in I, okay? So now if, for example, core number 2 tries to read, what will happen is that core number 2 gonna go through the M state to the valid state. And for the MI, what we're gonna, actually, let me start with write, because then it's easier to describe why we need read. So let's say number 2 wants to write to that cache, okay? So, so what will happen is that since I'm going to write to this value, if other cores has that value, they have to invalidate themselves. All right. So what will happen is that core number 1 going to switch from M back to I, because the copy that I have no longer valid. Core number 2 going to shift from I to M, and core number 3 is going to just stays in I. Okay. If, for example, core number 3 now needs to read something, what we need to do is that since we only have modified or invalid, and we cannot have 2 modified at the same time because you don't know which one is writing and which one is writing, what we need to kind of like, what we are forced to do is that R3 wants to read something, and all it needs to do is basically this guy needs to basically write back its value to the cache, invalidate themselves, and this one from I goes to M, and this one stays in I. So what I'm saying is R3 wants to read, and there's already another core that's written to the cache, and it's in the M state. What they need to do is write back their data, invalidate themselves, and then pass the data from the main memory to the new cache, the core number 3. So core number 2 transition from M to I. Core number 3 transition from I to M this time. Okay, so far so good. So now the final thing is that if somebody is in M and somebody else wants to read, what happens? So by the way, if you're in R3 and you have another R3, you just stays in M. So what will happen is that I am, because I'm the only one who has the data, I don't need to do anything. I have the most updated one. I just stays in M. Okay, so if you repeat something, you just stays in that stage. Then the interesting thing happens when we are reading from another one. So technically, I don't need to do anything because everybody is clean, right? The copy that I have in M right now is a clean copy. But since I don't have any way to distinguish between a dirty copy and simple copy in our caches, what I need to do is that if R1 comes in, R3 needs to invalidate himself, and core number 1 has to go to I. The reason for this is that if we don't do it, then for writes, we're going to have problem. If you have multiple M's, we don't know which one has the correct copy, dirty copy, and which one has a clean copy. Internally, they know, but externally, nobody knows which one has the correct copy, right? So because of that, we make the M an exclusive state, which means that only one person can be in M and everybody else has to be in I. But this is inefficient because in this case, this could have been that core number 3 could have stayed in M, okay, without any issue, because core number 3 had the clean value. It doesn't need to go back and write it back. If it has the dirty value, it has to invalidate himself. But in this case, it doesn't need to. But since we cannot distinguish between a dirty copy or a clean copy M, because M is just M for outside, then M it has to invalidate himself, and then only one core can go to the M. Does that make sense? All right. So this is obviously has one key problem, and that's the one that I just described, because there is one state that that everybody has a shared data, and that shared data is not dirty. Okay. So we don't need to invalidate ourselves if we have the clean copy and we are in M, and somebody else wants to come to M. What we can do is creating this new shared state that instead of just having M and I, we'll have M, S, and I, where in scenarios like this that we do 2 reads together, instead of going to invalidate, just go to S. And this one also goes to S. All right. So everybody is shared. The data is shared among the cores, but everybody has the clean copy of that value. So we call this an MSI cache protocol, the shared, the modified, and invalid. And if I want to repeat the same examples that I showed you before, let's say that all of them are starting from invalid state. Okay. And now let's say that R1 wants to read. So R1, since wants to read, instead of going to the M state, this time I'm going to the S state. The reason that I'm going to the S state is that I'm not going to modify this cache. I just want to read this cache. Okay. So I'm just going to the S state because we basically just said that I have this, I shared this with you, but all of us have the clean copy of this. So I, and I. And interesting things happens here is that if R3 wants to read, I1 will see that someone else wants to read, and I'm already in S, so I don't need to change myself. So I stay in S, core number 2 stays in I, and core number 3 goes into S. So in unlike M, which is an exclusive state, S could be shared among all the different cores. Okay, so core number 1 can be in S, core number 2 can be in S, and core number 3 can be in S. Okay, but now going back to the dirty clean problem. Now, for example, if R1 wants to write, what will happen is, since I'm writing to this, everybody has to invalidate themselves, right? So in this case, core number 1 has to switch from S to I. Core number 2 is already in I. And since I'm writing to this, I'm going to modify this cache. Now I'm going to the end. All right. So we're going back to what we described before. Now core number 3 is in M. Other cores are in I. Okay. So now, for example, if core number 2 wants to read something, what will happen is it's very similar to what I described in the MI stage. Since core number 3 has the dirty copy, it has to invalidate himself, go to I, write back the data, and core number 2 gonna go to S, and core number 1 gonna stay in I, right? So what's happening here is core number 3 is in the modified state. It has the dirty copy of that line. it sees another read from another cache, what it has to do is invalidate it itself, write back the data to the memory, go to the I stage, and the other one just wants to read, and reading, as I said before, is just going to the S stage. Okay? So the question is, why can't we go to the S states also? Well, we can do that, and there are ways. I mean, depending on how do we define this, we can say that. The only thing is, we typically, if we want to write back, we just write back and invalidate our stuff. But it's totally valid to do M to S basically, and I think even in our homeworks or in examples, we might do that. So depending on how we define this, I'm going to show you the states afterwards. And if we do that, that's totally fine too. Okay. This is also a minor optimization that you can do. Any other questions? So going back, so we're going to have a shared, a modified, and invalid state. The shared state is basically when you have a line that is clean, but it's shared among multiple cores. The modified one is when you want to write to that line. So you have the dirty copy of that line. And invalid means that I don't have that line or used to have it, but now somebody else wants to write it, so I have to invalidate myself. Okay? So we have M, S, and I, and we call this an MSI cache coherence protocol. What else do I want to say? Yeah. And remember about the dirty line. So remember, we had two different options. We had the write through and write back strategy. If we have a write through strategy, we don't need dirty lines at all. So whenever we write, we just write both memory and the cache. If we don't have, then we have the dirty bits. But in terms of your cache coherency protocols, nothing changes, right? So you basically, if you are in M, you have to go to the S, right? If you are in M, you have to either go to the I or to the S if somebody else wants to write it. If it's a write-through cache, then you don't need to write back things to the main memory because main memory already has it. You just have to transition from M to S or M to I, okay? If it's a write-back strategy, then you still have to do the same thing going from M to S or M to I, but you also need to write back data to the main memory. Okay, so that's the difference between write through and write back strategy. In both cases, you go to the M if you want to write, but if somebody wants to read it, you have to go to either S or I, depending on how they define it. All right. Any questions? Okay, so this is kind of like, state diagram of one core, depending on how we are having things. So for example, we are starting with the shared state. When we are reading, so when we don't have it, when we have a cache miss and we don't have it, if you want to read line Z, once we read it, we're going to go to the S state. Okay. If another core wants to write to that line, we have to invalidate ourselves and from S go to the I state. Okay. If another core wants to read it, then we just stays in our S state. If we ourselves want to write it, we have to basically upgrade ourselves from S to M. Okay. So if you want to write, we just have to tell everybody else that we want to write, so everybody else can go to I, and we're going to go to M. Okay. If we are into M and we intend to read or write from this memory, we just keep staying in M. Okay. If we are the only one who are in the M and we keep writing or keep reading, we don't need to do anything. We just stays in M. Okay. And finally, if somebody wants to read from the memory, as I said, depending on the structure, we can either go to the I or go to the S. In this particular case that I'm showing, if somebody else wants to write, we just need to go back to the S. But keep in mind that if this is a write back strategy, we have to write back first and then go to the S. All right, so that's the key point here. And then in M, if we are keep writing, keep in mind that if this is a write through strategy, then we have to write to the main memory as well. If this is a write back strategy, then I don't need to do anything. I just update my copy internally and keep my dirty bit equal to 1. Question?
Yeah, so, why do we write back or write if we're overriding state from M going to I?
Oh, this one? So the question is, if we are in M and somebody else wants to write in M, why should we write back to M? Keep in mind that we need to see all the, so there could be some other accesses in between for other cores or other lines that we don't see. So we definitely need to write to the main memory because there could be some instructions on the way between these two. From our perspective, we don't care, but there could be some other instructions for that is using those specific line that needs to read my write first and then the next write first. When we get to the consistency, we'll see why this matters, because the way the sequence of instruction that we write might matter of writing back things. Okay, does everybody understand this kind of like transition between all the states pretty well? Any questions? So to just summarize, we either in S, I, or M. If we are in I, if there is a cache miss, we either go to the S or to the M. If it's a write miss, I'm going to go to the M and start from M. If it's a read miss, I'm going to go to the S. From S and M then depends on the activity of myself and the activity of the other course. If I'm in S and somebody else wants to write, I have to invalidate myself. So I go from S to I. If myself wants to write, then I promote myself from S to M. Okay. So this is all with S. And if everybody else wants to read, I just keep in the S. All right. So I either stay in the S, go to the I, or go to the M, depending on different activities. Now let's say I'm in M. If I want to read and write, I just keep staying in the M, just have to be careful about the write backs. If somebody else wants to read, then I have to demote myself from M to S. Just again, I have to be careful about the write back. And if someone else wants to write, then I have to demote myself from M to I this time because somebody else wants to write, so I cannot stay in S. I have to go to the I. Again, I have to keep track of write backs, right? Say it again. The question is that with the write miss and write hits would be exactly in terms of implementation. It's kind of, so if you want to write, if you are already in M, you don't need to broadcast anything because everybody else is already in I. But if you want to go to the M for the first time, you have to broadcast it so everybody else can go to the I. So the only difference is the broadcasting part. In terms of the cache itself, doesn't matter. If it's a write miss, you go to the M. If you are already in M and wants to write again and again and again, you stay in M. Does that make sense? Okay. So let's see how we can improve our MSI. The one point somebody already mentioned, there are 3 more states that we can add to our MSI, and each one kind of help us in some cases. So let's actually go through those 3 additional states. But many systems, I mean, MI is very inefficient because MI doesn't have this S states that we really need in many cases. So we typically don't use MI, but MSI is really the minimum that you want to have in any cache coherent systems. And actually, if you want to have some coherency, you typically will have M, S, and I. So MSI is kind of like, the popular, the simplest way of having cache coherence. But modern systems actually typically tend to add a few more states for various reasons that I'm going to talk about in the next few slides. Okay. So the first thing that we're going to have is what's called an exclusive state, or E. The reason that we might need E is that, let's say that we are in S and we want to write something. Okay. But now consider this. So if you are in S and we want to write something, we have to tell everybody else that we want to write something. We're going to broadcast that we are writing something. But think about this scenario that we are the only one who is in S. Okay. In that case, we could have just silently go to the M without broadcasting anything, right? And if you think about this, is actually very, very common in many systems. If you don't have the line shared, like if you have line Z, mostly you will have that line exclusive to yourself, because most of the application doesn't really share the lines with each other, or most of the lines are just private to you. Okay. So the chances that this line is actually in the other cores are pretty low on average. But whenever you want to write, you just added this extra traffic to your bus to say that I want to write this, and nobody cares. You're just the only one that has this data. I don't care whether you want to read or write or do whatever you want with that line, right? So what you can do is adding this exclusive state that basically we are in E if we are the only one who has that data. And in that case, if we are in E and we want to write, then we can silently just from E go to M, and no broadcast at all. And this is very, very good for programs that doesn't share anything with each other, okay? Because we are saving lots and lots of unnecessary broadcasts, all right? So this will give us what we call an MESI. So I'm adding E to the mix. Soccer fan can call it messy. So basically, MESI is very similar to MSI. The differences are three. So on a read miss, okay, a processor can go from I to E if this is the only line that has that value. We have to check that, and there's a way for doing that. But instead of going from I to S, I can, if everybody else is in I can transition from I to E instead of going from I to S on the read miss. All right. If we are in E and if someone else wants to read, then I'm no longer exclusive. So I have to transition from E to S, okay? So that's an extra things that I need to know. And finally, the biggest advantage of this is that if I'm on E and I want to write, I can just go to M without broadcasting anything to anybody else, all right? So I'm silently go to M without saying anything to anybody. Versus in MSI, if I was in S and want to go to the M, I have to broadcast it to everybody else that, oh, listen, I'm going to go to M. Okay. Versus this one, if I'm in E, then I just silently go to M without saying it. So the question is that, does this include some overhead? Because when we are all in I and we want to go to the S or E, we have to kind of check. Yes, but it's very, very simple to check whether something is in I or not. So all you need to do, if everybody's in I, you're going to go to the memory anyway, right? So in memory, you can have just one bit that's showing that whether this line is shared or not. If this line is 0, then it means that you're good to go to BE. So when I bring in data, I'll just also check that flag, and I know that whether it's shared or not. Okay. And basically, my page table already has that information. All right. So for MESI, let's say everybody's in I. So let's see what happens with the sequence. So let's say, for example, R1 reads. So the difference between this case and previous cases is that since all of them are in I, then I1 goes to E instead of going to S. Okay. So now let's say, for example, R1 wants to read again. We keep in I, stay in I. then if, let's say, somebody else wants to write, since somebody wants to, sorry, this is I. Since somebody wants to write, I have to invalidate myself, and core number 2 has to go to the M, and I stay to the I. Then let's say, for example, R3 wants to read. I stay in the I. This one goes to the S, and this one goes to the S, and there is a write back happening here. Then if, for example, R1 wants to read, everybody goes to the S, S, and S, right? But there will be a scenario which that, no, actually I covered all the scenarios, I think. Yeah, there will be a scenario at this point here that if I'm in E and everybody else is in I, if I do write one, then at this point I go to M silently, right? So that's the only difference between this and any other cases, right? Or another scenario that could happen is if RR and then somebody wants to read R2, then in that case, core number 1 gonna go to S, core number 2 gonna go to the S, and core number 3 gonna go to the I. Okay. So I'm exclusive only if I'm the only one who has the data. If somebody else has the data, that person will go to the S. I will have to go to the S too. Does that make sense? All right, so that's number 1, the first optimization. The second optimization is what is we call an owner or O state. Okay, so if I'm in the I, if I'm in the M state, if I modify the cache, and of course everybody else has to be on the I state, and then now a new core wants to read data. Okay, and so who should provide that data to the new core? Should it be me or should it be the memory itself, right? So in order to kind of do that, we have a new state called O, okay? And this is the owner. And the reason for having an O is we call it this MOSI. So we are having the MSI and adding O to it. The M state is basically saying that if I am in the M and somebody wants to get the value, wants to read that value, in original case, I was in M, the other core was in I have to go to the S, this one has to go to the S, right? But how do I know who has to provide data, me or the main memory? Well, I add this O and say that, okay, if I'm in M, instead of going to the S, I'm going to go to the O. And this one goes to the S. And I'm going to the O means that I'm responsible for providing data to all the other cores. So I'm going to provide this data to the S. And not only that, the next time, for example, core number 3 is in I and wants to go to the S, since I'm already in O, I'm going to provide data to this core as well. I'm the one who is the owner of this data. I have the dirty copy. I really don't need to go to the main memory and write back this data. Instead of M, I'm going to go to the O, and I'm going to just provide this data to everybody. And this will, as you said, it's going to save a lot of bandwidth, because instead of this one goes so this one writes back and this one reads that value, I'm just going to forward it here and here, and I'm just going to keep forwarding that if anybody needs it. So I'm going to stay in O and everybody else in S, and whoever wants it, I'm just going to forward it to them because I'm the owner. All right. So 2 things that will happen is that if I'm on M, and if somebody wants to read it from M, I'm going to transition to O instead of transitioning to S, and the other core will transition to S. All right. And if I'm on O, if somebody else wants to write, then I'm no longer the owner. So I have to demote myself to I have to write back, and that the other core will go to M. Okay. We still need M and O because O is the shared state of a modified value versus M is the exclusive state of the same modified value. So the difference between M and O is in O, there are other cores that also has that data, but the data is provided by me instead of provided by the main memory. M is the exclusive states that's saying that I'm the only one who has that data. Everybody else is in I. Okay? Mm-hmm.
So why does the code for these two like data?
So the question is, if I'm in O and somebody else wants to write and go to the M, why should I write back? Remember, it has to be altered anyways, but again, remember that there are going to be some instruction in between that may not be. We need to see all the writes because there could be other cores that's, you know, the sequence of instructions might be different. Again, once we talk about the consistency, we'll see that. We want to read, remember, when we say coherency, we want to see the serialized write. We don't want to miss any writes in between, saying that, oh, in that case, you never do the write, right? So you always wait and say, okay, the next one going to be written and the next one going to be written. I mean, the write back strategy, the question is like, this is similar to the write back strategy. This is the write back strategy, right? So you want to minimize the write as much as possible until that you're no longer needed, you're invalidated, and somebody else wants to be replaced by you, right? So that at that point you need to write back to the main. Mm-hmm. Mm-hmm. Mm-hmm.
First core is going to get invalidated. Does that mean the core that wrote can go directly to E instead of M?
No. So the question is about E. So the question was if both cores are in S and one of them wants to go to the M, wants to write, should we go to the M or should we go to the E? So of course this one has to go to the I, no question about that. The question is, should we go to the M or should we go to the E? Remember, the difference between M and E is that E has the clean copy and M has the dirty copy. So if you want to write, you have to go to the M. You cannot be into the E. Any other questions? All right. So we have MOSI, and again, let's do invalid, invalid, invalid. Let's do read one. So we remember we don't have E in this case. So from I we have to go to the S. Everybody else stays in I. If somebody else wants to read, they also have to go to the S. So we stay in the S. That one also goes to the S. Then if, for example, write 2 wants to write, then this one goes to the M. Everybody else goes to the I. And the interesting thing happens here that if, for example, core number 3 wants to read, I go to the 3 goes to the S. 2, instead of going to the S, goes to the O. And core number 1 stays in the O and in the I. The difference is then here, instead of reading it from memory, we read it from M. Sorry, O. Okay, that's the difference. That it saves a lot of time. It's much, much more faster because we don't need to go through the main memory. We don't need to do the write. We just update it from S. And what happens afterwards is that, for example, if core number 1 wants to read as well, then the data will be also updated here. So this one goes to the S, this one stays in the O, and this one stays in the S. So again, data will be forwarded from O to the S. Okay? Does that make sense? And at some point, if somebody wants to write, for example, 1 wants to write, then this one goes to the M. This one has to go to the I, and this guy also has to go to the I. There will be a write back happening at this point. Okay? And the same story repeats itself, right? So you are in the M, so basically you are here, and the story repeats. Does that make sense? Another question is that can we use E and O at the same time? And the answer is yes, you can have MOESI. You can actually have benefit of E and O at the same time. The reason is, for example, in this case, if we had E, instead of switching from I to the S, we could have done I to the E. And in that case, we could have had the silent upgrade from E to the M. So O and E does not have to be exclusive. They can work together. So we can have an MOESI coherence algorithms if we want to, and basically having all these 5 states together. All right. Any questions? All right. So there's one more state. I'm going to pause here. I'm going to talk about it the next time, and that's called forwarder, which for the shared state. So I'm going to pause here, talk about that in the next time. All right.